Hello and welcome to this third lecture in this series on molecular structure and spectroscopy. Today I'm going to be talking about linear combination of atomic orbital theory, or LCAO theory. Chemical bonding, up till now we've really been thinking of in terms of Lewis theory. So electrons are shared between atoms in order that each atom is then surrounded by 8 electrons, so the so-called octet rule. Of course this applies for all atoms except for H and helium. This successfully describes the bonding in simple molecules, things like water, hydrogen fluoride, hydrogen, and so on. And it explains why noble gases are inert. And it can also explain simple ionic compounds like sodium chloride, where we have sodium ions and chloride ions. But there are a lot of problems with this approach. Let's now go and have a look at some of these. So, in particular, some molecules are difficult to deal with, and they have to be drawn instead as resonance structures. So an example of this is something like ozone, which you end up drawing something like this. So you have you'll have a minus charge here and a plus charge here, and then this resonates with the resonance structure of this. So that doesn't work in Lewis theory. There's a problem. There are also lots of molecules where the octet is expanded. So things like if we have the sulfate anion, SO4 2-, we've got more than 8 electrons around the central sulfur. So how does that work within this theory? It doesn't. There's also molecules consisting of bonds that cannot be described in terms of simple pairing of electrons. So a simple example of this is something like B2H6, so where it's often drawn like this. So some sort of sharing of electrons between two molecules, but this can't be described in terms of Lewis theory. There's even more problems. So how about the existence of molecules with unpaired electrons? So we can have molecules like NO, that has an unpaired electron. Or we can have stable radicals, which are reactive, yes, but are stable. So things like OH, which you'll have seen in atmospheric chemistry. Also, the Lewis octet theory doesn't tell us anything about the shape of the molecules. So we can draw a CH4 molecule like this, and we can put our dots and crosses in. But it doesn't tell us anything about what this molecule looks like in 3 dimensions. And it doesn't give us detailed information about the bonding either. So things like the O2 molecule is actually paramagnetic. So that can't be described using Lewis theory either. Finally, electron spin, so the thing which actually pairs electrons together, wasn't even known at the time. So it was really developed as an empirical theory to explain things. But with the appearance of quantum mechanics, we can actually understand bonding more accurately, and that's what we're going to go on and look at now. So in particular we're going to look at LCAO, or linear combination of atomic orbital theory. Now before I start, I should say that a linear combination is when we have terms which are added together and multiplied by factors. So if I had x, y and z as 3 variables, a linear combination of these 3 variables might be 3x plus 4y plus 2z. That is an example of a linear combination of terms. If we think about orbitals, then we can write an equation like this. So this here, capital psi, is our overall wave function. Phi here with subscript n are our atomic orbitals. And these Cn here are just constants. And these constants determine the weight of these atomic orbitals in the linear combination. So up here we've got the 3, 4 and 2. These are the constants in this linear combination of x, y and z. And here we just sum over all atomic orbitals. So we can write the total wave function as a linear combination of atomic orbitals. We now need to go and put that into practice. So what we're going to do is have a look at the H2 molecule and work through the molecular orbitals, the linear combination theory. So what we're going to do is use a so-called minimal basis. So basically, to understand the bonding in H2, we've got two atoms, HA and HB, and we're going to look at this bonding in terms of the smallest set of atomic orbitals possible. So we're going to use the 1s on atom A and the 1s on atom B. So using the LCO equation we saw on the last slide, we can write the total wave function is going to be a linear combination of the two individual atomic orbitals. You'll remember we often like to work with the wave function squared, and in the wave function squared we'll get terms involving c squared. Oh, sorry, I should have put a and b here rather than 1 and 2. So ca squared has to be equal to cb squared in this case because the molecule is symmetric, so we'd expect ca and cb to be the same. This actually gives us two possibilities. So we have Ca equals Cb, or we can have Ca equals minus Cb. We're going to now look at the case where for Ca equals to Cb. Now, the first thing we need to do when looking at this linear combination is actually try and work out what Ca and Cb are. And the best way to do this is by remembering that molecular orbitals or atomic orbitals need to be normalized. So if an orbital is normalized, this means the integral of the orbital over all space has to equal to 1. So this means that electrons are in the orbital somewhere. So now we can substitute it in here for the wave function. So let's write this in here. So the wave function squared, so we can have Ca1Sa plus Ca1Sb multiplied by Ca1Sa plus Ca1Sb d tau equals 1. So here we've used the fact that Ca is equal to Cb, so we've only got Ca's in this expression. What we can do now is multiply these brackets out, so we end up with integral, and we end up with an integral of a sum of terms. And we can actually, if we've got an integral of a sum of terms, we can just separate them into the individual integrals of each of the terms. So what we get here, well, let's write the next stage in the line first. So we've got Ca squared 1Sa squared d tau plus integral of Ca squared 1Sb squared d tau plus integral of Ca squared 1S A 1SB d tau plus integral of Ca squared 1SB 1SA d tau. We can see, and all of that is of course equal to 1. What we can do now is take out the Ca squared as a factor, so let's simplify things. We'll write Ca squared, open big brackets, integral of 1sa squared d tau plus 1sb squared d tau plus 1sa 1sb d tau plus integral 1sb 1sa d tau, close brackets. All of that is equal to 1. Now we can make a couple of simplifications here. So we actually know that the atomic orbitals are normalized already, because, well, we can use normalized atomic orbitals. So the integral of 1sa squared dt is just equal to 1. So that's equal to 1. The same for the 1sb orbital. It's equal to 1 because it's a normalized atomic orbital. 1s and 1sa and 1sb are the same, so actually these terms here are equal to each other. And what we can do is just approximate, and this is just a number actually, so we can set this equal to this thing called s, so and just call it a constant. So right, I'm going to go on to a new slide. So I'm going to rewrite the equation. So we had a Ca squared multiplied by 2 plus 2s is equal to 1. Okay, so here I've substituted in s from before, and I've put together the two ones from the normalized atomic orbitals. This thing here, s, is the so-called overlap integral. And if you actually work it out, it's just a number, it's just a constant. So now we can actually rearrange this equation here to get Ca. So Ca is going to equal 1 over 2 plus 2s, the square root. Okay, so I've just rearranged this equation to make Ca the subject. So now we know what Ca is. We know that our bonding orbital, so because we've looked at the example where we've had the orbital on 1sa is in phase with the orbital 1sb, so they're the same colour. The outer phase one would have been this one, 1sa, 1sb, and that one's coloured in. So this is the one with minus, but we're looking at this one here with the plus. So we can write here psi plus, and this can also be written using a symmetry term, so it's psi g, so for Gerada. I'll come back to that later on. So this was equal to, remember from the beginning, we had Ca 1sa plus Ca 1sb, and this is equal to Ca, let's go back, sorry, sort this out, Ca 1sa plus 1sb, so this is equal to 1 over 2 plus 2s to the half multiplied by 1sa plus 1sb. So this is the final wave. This is the final wave function. This is the bonding wave function of the H2 molecule. Let's move on. I've left a blank slide just in case I needed to make some more space. So I've got some homework for you now. So using exactly the same approach, you should be able to show that the antibonding orbital of H2, so this is the one where you've got this 1sa minus 1sb instead of a plus, will have this form here. So I've used psi u here, but this could also be written psi minus for the minus sign over here. Okay, so that's a piece of homework for you to try. So it should be reasonably straightforward. So now we've got the orbitals, we actually need to calculate the orbital energies. So to do this, we can use the Schrodinger equation, because it says if we make the Hamiltonian operator h hat act on psi, it gives us the energy here multiplied by psi, and this the energy is what we want to get. So we need now to actually solve this equation. So we're going to do this in sort of a reasonably simple way. we've already got an expression for psi because we've just worked it out, so we can actually work out the energy. Okay, let's start doing it. So we've got our Schrodinger equation, H psi equals E psi. What I'm going to do first is I'm going to multiply on the left both sides with psi. So this gives us psi H psi equals psi E psi. Now, we need to multiply on the left because the operator, H is an operator, so it actually acts on the wave function. So we can't put a psi into here because this psi, these things belong together. E, on the other hand, is just a constant. It's just a number. It's the energy. So we can actually rearrange this side, and this gives us E times psi squared. And psi, we know we've already normalized. So we've set. So if we were now to integrate both sides, so if we were to integrate psi H hat psi d tau equals integrate E psi squared d tau. E is just a number, so it can come out of the brackets, out of the integral sign, sorry. We know this term here is equal to 1. So this becomes just E. So we have overall this integral here is equal to E over here. Now we need to work out this term here. So let's put it in. So let's get quite a big an equation now. So we've put in our term from before. So we get 1 over 2 plus 2s to the half, 1sa plus 1sb. Then the Hamiltonian operator. Then 1 over 2 plus 2s to the half, 1sa plus 1sb d tau equals E. Now we can start to tidy this up a little bit. So this thing here and this thing here are just constants, so they can come out of the integral. So we can now write 1 over 2 plus 2s, because when we multiply them together the square root sign disappears. Integral of 1sa plus 1sb h hat Hamiltonian operator 1sa plus 1sb d tau is equal to E. What we need to do now is multiply out these parentheses here. So if we now do this, we get 1 over 2 plus 2s, and let's actually big brackets, and so I'm going to multiply out the brackets, and I'm going to do the integral of each of the terms in turn. So I'm going to get integral 1sa h 1sa d tau, so that's these two terms, plus integral of 1sa 1sb. Oops, sorry, I've missed a let's cross that out. Integral of 1sa h hat 1sb d tau plus integral of 1sb h hat 1sa plus integral of 1sb h hat 1sb d tau, and all that is equal to E. So I've just multiplied out these brackets. What I need to do now is actually work out these terms. Well, each of these terms are actually just numbers, so we can replace them with an abbreviation. So what I'm going to do is the integral 1sa h hat 1sa d tau. I'm just going to call this HAA. So you'll notice there's no hat on here, and it's actually just a number. But we know the 1s orbital on atom A of the hydrogen is the same as the 1s orbital on atom B. So HAA is also equal to the integral 1sb h hat 1sb d tau, sorry. The other simplification I'm going to make is I'm going to say that the integral 1sa h hat 1sb d tau, I'm just going to call this HAB. And because atoms A and B are the same, we can also, this is also 1sb, sorry, b h hat 1sa d tau. So we've now got two terms to simplify it. So going back to the equation before, so I've got 1 over 2s plus 2, sorry I've written that the way around, let's just cross that out, 1 over 2 plus 2s, that makes it look exactly the same for you, open big brackets, I've got HAA plus HAA plus HAB plus HAB equals E. And then I can simply simplify this, so 1 over 2 plus 2s, 2 HAA plus 2 HAB is equal to E. And now, of course, I can just cancel out all these 2's, so I end up with 1 over 1 plus s HAA plus HAB equals E. And just to remind ourselves which orbital I was talking about, I'm going to put E plus, so this is the bonding orbital of the H2 molecule. So here we have the answer for the energy of this orbital. I left myself a couple of blank slides. So now, in exactly the same way, you should now be able to go away and show that the energy of the antibonding orbital of H2 can be written in this way. So here we know it's the antibonding orbital. We've got a minus sign here, so I could also write this as E minus as well as EU. So here we are at the end of this lecture. So I'd like you to go away, do these homework tasks, and then also complete the Blackboard test associated with this lecture, and then I will see you in the timetabled session. That brings me to the end of lecture 3.